again. We did infrared spectroscopy, we did mass spectroscopy, fragment analysis. The last of the A-level spectroscopies, and there are many more spectroscopies in the wider world of chemistry, is shortened to NMR. Stands for nuclear magnetic resonance spectroscopy. At A-level, more of it is about, here's the results, what do they tell you? That's my neighbour banging around with some metal. It stands for nuclear magnetic. Why? Because nuclei have a spin for each of the subatomic particles, that's a neutron or a proton, in the nucleus. So that's the magnet derived from that. There's a kind of little catch to it. I'll tell you about that in just a second. The resonance, I'm not sure quite what the word resonance is used, but like I said, it's not so much about what happens, it's more about, here's some results, let's interpret them. So which part of the electromagnetic spectrum, oh, have you got your stuff ready to take notes, because you're going to need to do that. You're good, right. So more of that later. So which part of the electromagnetic spectrum? I did mention this a couple of videos ago, I think. We are talking very low energy, the low energy part of the electromagnetic spectrum, because the changes involved in NMR require very small amounts of energy. So it is an idea that it's a good idea to know some idea of what's going on. The actual complexities of it are beyond A-level and beyond me, to be quite frank. So we do a very sort of simplified explanation of what is going on. There's a lot more to it, and the final result of that is MRI imaging, which is, I have no idea how that manages to achieve it, but it's fantastic that it does. So first of all, there's a nucleus type that does it, and the key thing is it has to be odd. Now that doesn't mean the RAM on the periodic table, because that's the weighted mean of all the various isotopes. What it refers to is you pick a particular isotope, and if it has an odd number as its mass, here's an example that you'll get to be familiar with. Carbon-13. I have a little trouble with the camera, but we'll carry on. Odd numbered nuclei, meaning the isotope has an odd mass. So like I said, carbon-13, 6 protons, 7 neutrons, total 13. Now each one of those 13 has a spin. It has a spin of plus or minus a half. That's a bit ask a physics teacher, quite frankly. So that when you have an even number, the spins cancel out. There's as many plus halves as there are minus halves. When there's an odd number, one of them is left over. And that gives you a nuclear spin. Now in the world of physics, when a magnet is spinning, it generates electric fields. When an electric charge is spinning, which is a nucleus, it generates a magnetic field. So that's where the nuclear magnet comes from. It's the one half over spinning, generating a magnet. What else? Well, at A-level there's only two that we look at. Carbon-13 and hydrogen. There's a whole load more. I mean, there are loads and loads of isotopes with odd numbers. I mean, some of the other ones that people in the paid world of science. Nitrogen-15, not the most common isotope of nitrogen, it's 14, but nitrogen-15 does it. I remember doing platinum, I think it was 195, it was a long time ago. And so they would do it, but we don't do those at A-level, we don't need them. We just, at A-level, look at those two. We'll do that one first because it gets us in the right frame of mind, and we'll do this one when it's got a lot more to that one. And we're only doing the explaining video to start with. We'll do the interpreting videos for carbon-13 and then on to what is called proton NMR, because that's a proton. But we need a simple explanation of what goes on. So I'm just going to get the board ready for that. I'll see you after the edit. So the simple explanation is, once you've got a odd number of nucleons, you get the spin resulting in a magnet. Now we can, in very simple terms, represent these atomic spin magnets as arrows. Now if you remember back to the days of joyous early science, magnets, you put two magnets down, push one towards the other, they have one flip round so that they go north-south, 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 so they all sort of line up, don't they, magnets? What they're doing is they're aligning with the magnetic field. That's what magnets do. If you want them to go north to north, you have to put energy in and force them together. If I use these two pens as an example, if these two magnets are north with the pen cap, okay, so they would line up like that with each other. If you want them to do that, you have to put energy in and physically hold them in place. And when you let go, it flips back the other way. It moves because it doesn't want to be in this, well, you could call this a high energy state, which is what this represents on the board. So when you talk about NMR, you have a big external magnetic field done with coils, electromagnet. Turn the machine off then. Big external magnetic field, and you put your sample in, and the nuclear magnets line up with the magnetic field, a bit like, you know, same sort of idea as the pen really. And if you put in the energy, depends which symbol you use for frequency, if you get the right energy, it will go and do this to the magnet. Now I've only drawn 4, you can imagine there are billions upon billions in an actual sample. So you will make it do the opposite alignment. And when you find out the energy that requires, that tells you something about, well, the nucleus and what you've got around it. And then when you turn the magnetic field off, they'll flip round, or if you turn the energy off, they'll flip back. Now there is a real thing in the real way it works, is that you also look at when they flip back and they release the energy back again, but we don't get into that. The simple way to think about it for A level, it's enough, is to go, they all line up, how much energy do I need to put them in the anti-state where they don't want to be, and that will absorb out of the radio frequency range, and that will tell you there's been a flip. It's called a resonance when they flip round. So quite frankly, that's enough of an explanation. So you need some notes on that, because just in case there is a simple question. So make sure you know, firstly, the type, which I said was odd. 2, that you're flipping atomic magnets round. We're going to take a quick edit, and I'll see you after the edit. Now, the key thing about NMR is it tells you a lot of information. Now, the thing about it telling you a lot of information means it's a little bit more complicated to interpret. Unlike infrared, where you just look at the spectrum and go, oh, that matches that, that matches that. I mean, there is an element of that in it, but as you get into proton NMR, there's got to do quite a bit of deductive reasoning. But it all stems from environments. So when you look at a molecule, we'll take a simple molecule. You look at that, okay? Now, in your NMR machine, you would either be looking at hydrogens or you would be looking at carbon-13s, because both of those have an odd count of nucleons. So let's say we're doing carbon-13 NMR. So when you look at the displayed formula of that, which is ethanol, environments means what is around the atom that you're looking at. So if we're looking at this atom here, I'll call it carbon A. It is surrounded by 3 hydrogens and it's joined to 1 carbon. Environment A. If you look at this carbon, it is joined to a carbon, 2 hydrogens and an oxygen. That's not the same. That's a different environment. The consequence of having different environments is that the energy required to flip the magnet for this carbon is not the same as the one to flip that one. So therefore, in doing that substance as an NMR, you would get 2 radio frequency absorptions. The actual energy difference between these two is not massive. And so, we don't measure it in terms of joules, it's too tiny a difference. We have an unusual unit for perhaps when you consider what this is. So the unit used in NMR spectra is ppm, parts per million, which I feel some people who I teach with dread. I think you know who you are. And you don't have to do the calculations associated with it. It is just because the difference between the frequencies are quite small, and so you do it as a parts per million to make the number larger to manage and actually have a handleable number that isn't 3.2 times 10 to the minus 15 or something like that. You want a really small. That's too small, but you don't want a tiny thing. So you do it in parts per million to make it a more recognisable number and a more manageable number to work with. So it's about environments. If you were looking at protons in this thing, those are the same, those are different, and those are different. So there were 3 hydrogen environments. But we're not going to do proton NMR. The video that follows this one is going to be carbon-13 NMR. So the unit looks like that. What does an NMR spectrum look like? Well, it would look like that. Quite frankly, what does it look like? It has a scale along the bottom. This is the ppm scale. It's called delta, which is annoying because we use delta for partial charges, and it's called a chemical shift. It's a shift caused by the structure of the chemical, and there's the 2 lines. That, as it turns out, would be A, and that would be, as it turns out, to be B, but we are not getting into all of that and why that is. That comes in this next video that follows this one. So this will be the ppm scale along here. You'll notice they're the same height, because one of the things that NMR does is it counts how many there are. So there is 1 carbon in environment A, 1 in B. If they weren't the same height, it would tell you that there would be more than 1 in one, less than the other. And that's kind of enough until we start actually analysing the videos. So thank you for watching. There are no questions with this because the questions are about interpreting, because A-level, carbon-13, if it's in your A-level course, and for many courses now it is, proton NMR, hydrogen NMR definitely is in every course. And there'll be another set of videos about that, and that's a little bit more complicated, take more than one video. And I'll see you for the follow-up video to this, which I'm making straight away, about interpreting carbon-13 NMR. Thank you for watching, I'll see you soon. Bye bye.